There are not so many results or statements about phase transitions that are universal and that apply to a wide range of phase transitions. You usually have to investigate specific systems and learn about the properties of the phase transitions in these specific systems. But one of the few general results that you can derive is the so-called Gibbs phase rule. And to prepare you for that, I would like to consider systems very generally that can have different phases and moreover that are composed of, that are mixtures of particles or molecules of different type. Say, we can have a phase 1, we can have a phase 2, we can have a phase 3, and so on. So in total, let's say we have m different phases. This might be solid, this might be liquid, and the third one might be a gas phase, and there may even be more phases. And the substance may be a mixture of different types of molecules. So, and in each of these phases, you may have a molecule A, and you may have a molecule B. Yeah, so the blue one is, say, molecule B. And there might be others. And let's say that in total, you have L different molecules. Now, in each phase, you have a certain number of molecules of a certain type. And you can define the relative abundance of a molecule type L, where L goes from 1 to capital L, in the phase M, where M goes from 1 to capital M. So let me indicate this in this form. It's little n with two indices, M and L, and it's defined in the following way. It's the number of molecules of type L in the phase M divided by the total number of particles in phase M. The total number of molecules or total number of particles in phase M, this is the sum over all molecule types of the number of molecules of type L in phase M. Now, in general, this relative abundance of molecule type L may vary between the phases. So imagine you have a mixture of two substances, I don't know, water and alcohol, and you can have a gas phase and a liquid phase and a solid phase. And in the three phases, you can have different concentrations of alcohol. And there's no reason why the concentration of alcohol should be equal in the three phases. So this relative abundance may vary from phase to phase, and the relative abundance is an intensive variable. It doesn't change, it doesn't scale with the size of the system, it's an intensive variable. And finally, this whole system, composed of various phases and various types of molecules, this whole system is coupled to both a heat and a volume reservoir. So this is happening, say, in open air, and this controls the temperature and the pressure of that system. And now we are wondering how many of these phases can coexist, and which conditions must be satisfied for the coexistence of these various phases. And first of all, we can look at the number of independent intensive variables that we have in this setup. Well, we have m phases, we said. There are m phases coexisting. And now for each phase, in each phase we can have L different types of molecules at different concentrations, and the concentrations may vary from phase to phase. And in each phase, the concentrations of the various molecules are characterized by these relative abundances of the molecules. We have L different molecules, so we have L relative abundances, but they are not all independent because they must add up to 1. So only L minus 1 of these are independent. So in each phase, we have L minus 1 independent relative abundances. Only L minus 1 of these are independent because they must sum up to 1. And each of these independent relative abundances is an intensive variable. So we have L minus 1 independent of these for each phase. We have m phases. So this gives us m times L minus 1 independent intensive variables relating to the concentrations of the different molecules in the various phases. And then in addition, we have temperature and pressure that are controlled from the outside. And these give us two additional intensive variables that are independent of these relative abundances. So we have 2 more. And these 2 more relate to pressure and temperature. So this is the total number of independent intensive variables in the system. Now, in order for these phases to coexist, certain coexistence conditions must be met. We had learned earlier, when we talked about one type of molecule only, one substance only, that the coexistence condition is that the chemical potentials are equal. So that the chemical potential in phase 1 must equal the chemical potential in phase 2. And if we have more than 2 phases, this generalizes. The chemical potentials in all the phases must be equal. So this must also hold for phase 3 and so on up to phase M. These must all be equal. Now we have L different molecules, and each molecule occurs in each of the phases, and each molecule has its own chemical potential, and coexistence presupposes that the chemical potentials of all the molecules must be equal in all the phases. So in fact, this must hold true for all the molecules. So for all L going from 1 to capital L. And therefore, we have several independent constraints, and the number of independent constraints on the chemical potentials, and hence the chemical potentials are also intensive variables. So the number of constraints we have on intensive variables is the number of different types of molecules, because we have these constraints for the chemical potentials for all molecule types, and we have L of these. And for each molecule, we have m-1 equalities. Yeah, we have there appear m different chemical potentials. Yeah, for a given molecule type, there are m different chemical potentials for the m different phases, and there are m-1 equal signs, so these are m-1 constraints for each type of molecule. So in total, we have L times m-1 constraints, L times m-1 coexistence conditions. And then the Gibbs phase rule says, if we look at the number of independent intensive variables that we have, that's the formula given above in the first line, and we subtract from that the number of coexistence conditions, the number of constraints that we have on the intensive variables, this difference, this is the dimension of the coexistence manifold. When we require coexistence of these m phases, then we have these L times m-1 constraints. We subtract that from the number of degrees of freedom that we have for our intensive variables. Yeah? And then what remains describes the dimensionality of the coexistence manifold. I'll show it in a minute in specific examples so that you have a more visual idea of that. And so you have coexistence on a manifold. And you can consider a space spanned by all the intensive variables that you have in your system. In the systems that we considered so far, these were simple systems. We only had two intensive variables, namely pressure and temperature. So this was a two-dimensional space. Yeah, so this PT diagram, the T and the P axis span the two-dimensional space. And then we had coexistence on a curve. And we had a coexistence curve. And this is a one-dimensional manifold. Yeah, it's characterized by one parameter. And now we are generalizing this. We have more intensive variables. So we no longer have just a PT diagram and spanning a two-dimensional space, but we have more intensive variables spanning a higher dimensional space. In this space, then we have constraints. If we have coexistence conditions, and this reduces the dimensionality of the manifold on which you can have coexistence of phases. And the dimension of that manifold, that's the difference of the number of independent variables minus the number of constraints. So it's m times L minus 1 plus 2 minus the number of constraints, which is L times m minus 1. And this difference is L minus m plus 2. And this formula here, this is the Gibbs phase rule. And to make this more concrete for you, and this is the last slide for today, let's consider a few examples. First example, what we've considered so far are simple systems that are composed of a single type of molecule only. So you have only one component, L is equal to 1. For example, you have pure water, so you have only water molecules and no other molecules. And let's say you consider coexistence of two phases, m is equal to 2. So you have two different phases, for example, liquid and vapor. This means that you have only two independent intensive variables, namely temperature and pressure. There's only one component, so there are no relative abundances. You only have as intensive variables temperature and pressure. Now at a phase transition, we found only one coexistence condition, namely that the chemical potentials of the two phases must be equal. So in our example, that the chemical potential for the liquid and the chemical potential for vapor must be equal. Then the Gibbs phase rule tells us that we have coexistence of the two phases on a 2 minus 1, that's equal to 1, on a one-dimensional submanifold. One-dimensional manifold is a curve. And indeed, phase transitions that we had looked at so far, we have the PT diagram, and different points in this PT diagram correspond to different states of the system. But you have coexistence of the two phases, liquid and vapor, only on a curve, which is precisely the coexistence curve. So the Gibbs phase rule tells us very generally that this must be a curve. It's not a point, or it's not the entire two-dimensional space. It's a curve. We could still look at the case where we have only one component, so say still water, but now we could ask what happens when we have three phases present. So the number of phases is equal to 3. So liquid, vapor, and also solid. Then the Gibbs phase rule tells us that we can have coexistence of these three phases, liquid, vapor, and solid. We can have coexistence on a submanifold of dimension L minus m plus 2. Now in this case, L is 1, m is 3, so L minus m plus 2 is equal to 0. So we can have coexistence only on a manifold of dimension 0. A manifold of dimension 0 is a point. A point has 0 dimension. And indeed, when you look at the phase diagram of water, you have here the coexistence curve for liquid and vapor, but then you also have at low temperatures or high pressure, you have the solid phase, which is ice, and there are coexistence curve roughly of this shape. And there's one point here. There's one point where you have coexistence of all three phases. This is the point that the Gibbs phase rule indicates. This is the so-called triple point of water. Yeah, so indeed, the Gibbs phase rule tells you this on a very general basis without requiring any specific model for water or for any specific substance. It tells you very generally that if you have a single component only, you have coexistence of three phases, then this can only happen at a point. You can use the Gibbs phase rule to answer questions like the following. You can ask the question, how many phases can coexist at most for a mixture of two components? So say you have two substances that you mix, I don't know, alcohol and water or something else. You have a mixture of two components and you wonder how many phases can coexist at most when you have such a mixture. The answer is it's not only the three familiar phases that you know from water, liquid, vapor, and and solid. But you can, when you have a mixture of components, then you can have more phases. Now, what is the condition that must be satisfied so that m phases can coexist? The number of degrees of freedom that you have available, which was given by the Gibbs phase rule, L minus m plus 2, well, that must be non-negative. Yeah? If it's 0, then you have a point. If it's greater than 0, you have a curve or a higher dimensional manifold, but it must not be negative. You can solve this inequality for m. You find that m can be at most L plus 2. Well, if you have a mixture of two components and L is equal to 2, then L plus 2 is equal to 4. So for a mixture of two components, you can have at most 4 different phases coexisting. And if they do coexist, then they coexist at a point, like the triple point of water.